This is lecture 18 on the topic of homomorphisms. It's part of a pure mathematics course on finite group theory at junior and senior level, and the first author is Barnard of the text that I'm using. It's in the Teach Yourself series and called Mathematical Groups. If you'd like to know more about the text and the course, go to this website. So Prof. Hugo deGaris, Prof just short for Professor, Hugo deGaris is my name, .wordpress.com, and then click on the tab deGarisMPC, so Mathematics, Physics and Computing. So graduate level courses in mostly pure math and math physics. Okay? And if you'd like to email me, I'd appreciate feedback. Here's my email address, so just Prof. Hugo deGaris, which is just the same as in the link to my website, profhugodegaris@yahoo.com. Now this is the second last lecture of this lecture set, this course, the first, I hope, of literally hundreds over the next decade or two or three, if I live long enough. So this one, the topic is homomorphisms. But before I get into the nitty-gritty, perhaps I should say, perhaps you've noticed a few changes. The background books maybe look different, something looks different, and the lighting may be different. And the reason for that is I am right now, not recording this in the living room. I'm recording this in the bedroom. And the reason for that is, recently, my eyes have been getting sore, and I've been trying to figure out, what's the reason for that. One is maybe just too many hours in front of the computer processing all these videos. That's one hypothesis. Another one was the bad lighting in the living room. Third one is maybe I just need reading glasses. So yeah, I'll chase that up. I'll buy some reading glasses. So what's happening right now is an experiment, trying to see whether the new lighting, well, the lighting just above here in the bedroom is softer. It's masked. It doesn't involve raw bulbs that I think are too bright, locally too bright. So it's an experiment. Now, if I find by doing it in the bedroom that my eyes do not hurt so much, fine. The potential downside of filming in the bedroom is that the bedroom faces out maybe 50 meters or so onto a main road. So there might be some traffic background noise, which could be annoying. I just need to do an experiment to see how loud it is. If it's too loud and too annoying, well, I'll just go back to the living room and just change the lighting, just pay for that expense. Occasionally an aeroplane flies over, you may hear that. Okay, so this is an experiment. Like this is the very first course of hundreds, probably, very probably, in the series, in the deGarisMPC series of graduate level math physics and pure math courses, and a few computer theory courses thrown in, maybe 10% or so. All right. So as you're probably well aware now, I'm trying to provide a PhD second year, in fact, PhD 2 level education in pure math physics for free. Yeah, just by making all these lectures. It's my new career. I'm an ARCer now, A-R-C, after retirement career. And I feel what I'm doing now is hugely more significant than what I was doing when I was a waged, in other words, being given a salary professor, because then I'd teach 20 students or so. And rather cynical of being a researcher, because I also read that the average research published paper is read by one other person. So if you let that sink in, I mean, this industry, huge numbers of researchers churning out papers for what? To be unread? So it made me somewhat cynical. So now that I'm arcing, I'm free, I do what I like, and I feel what I'm doing now is hugely more significant. Okay, well, let's get down to nitty-gritty for lecture 18. A homomorphism. Now, we've already done isomorphism, so probably you suspect that the two concepts are linked somehow. And yeah, that's the case, they are somewhat similar. But the definition of a homomorphism, so effectively same shape, same form, is that the definition of the homomorphism is just the same as the isomorphism, but you drop one condition. So the definition of a homomorphism is more liberal, it's less constrained than the definition of an isomorphism. And what is that one condition that you drop? Well, you drop the criterion that the mapping between two groups has to be bijective. So a homomorphism, you don't have this, you throw that out. Okay? So in practice that would mean, for example, you could have like many to one mappings. Okay? Right, so a bit of revision to motivate the definition of a homomorphism. So I'll go through the definition of an isomorphism, because homomorphism comes out of this, right? I hope you can see this clearly enough. This is different lighting, so I hope this is okay. Right? Well, so let's see, what chapter was that? Chapter 11 on isomorphism. Chapter 11 in your text, if you're using the text, right? So two groups. So here's your set G and your binary operation little circle, but it's a hollow. In other words, this is a hollow circle, and this one is a filled-in circle. So you have two groups, G and H, with binary operator little circle, whatever it is, and another binary operator filled-in circle. They're just symbols. Okay. Now for an isomorphism, you have a bijection between these elements. So it's a strict one-to-one mapping. So one element this maps to one element in this, right? That's the case for isomorphic mapping. When your function here is isomorphic. But when you have homomorphism, you do not have to have this isomorphic, one element maps to one element criterion. You throw that out. You don't need it. So you could have many to one. You could, and I'll throw out the question to you, an open question, perhaps question. Could you have a smaller group, like if G is smaller than H? Could you have? Once you understand what a homomorphism is, think about this question. You can certainly have many to one. So you'd have a larger group mapping to a smaller group, H. How about the other way? So leave that as an ongoing project for you. What about if G is actually smaller than H? Now that mapping obviously cannot be surjective. Right? Surjective means that every element of your codomain, your target set, if you like, gets mapped to. Well, that's not possible if your group G is smaller than H. So once you understand what a homomorphism is, a particular kind of mapping on F, the function F, can that function be homomorphic if G is smaller than H? Now, it will work if G is larger than H, and homomorphism is sort of more general. Isomorphism is more specific, more constrained. So you can have homomorphisms that are isomorphisms, but in general, an isomorphism is not well, it's more restrictive than a homomorphism. All right, so an isomorphism is, so firstly you have a bijection between the elements of these two sets, right? So one maps into the other. That's for an isomorphism. So f is your function that maps this set into this one, okay, such that for any element belonging to G and for any element belonging to H, that the binary operation on oops. I should check more carefully. Okay, so for any two elements in your set G, you perform a binary operation on those two elements, and when you map it, you get this result. I'd call that in earlier lectures the F of Mn criterion for isomorphism. Now here's where the revision comes from. Where does this criterion come from? What's its motivation? Well, you're performing a mapping between two groups, right? So it's not enough just to map elements, you know, from one group into elements of the other group. You also want the corresponding entries in the group table to map. So if this is group 1, say G, and this is the group table of your second group, H, then GI, binary operation GJ, will give you GI, little circle GJ, right? That's the result of your binary operation on these two elements of big G. Now you want that to map to the corresponding element in your second group, right? So this is group H. So this element here, let's say, is HM, and this is element HN. So this element here will be HM binary operation. Now which binary operation? Well, of the second group, the filled in circle, if you like, right? The second